Today I'm happy to give you a presentation about some of my previous work, that is learning electronic structure from X-ray spectroscopy using multiply theory. And of course, the data is always an element, a very, very important element in the study, and why we need high performance computing for such kind of study. Today's talk, I will mainly talk about the three main aspects. Like the first part, I will introduce briefly why we need X-ray spectroscopy, how we can use it to decipher the material properties. And then the second part is going to after we have such measurement or experimental spectroscopy, how we should interpret the results. And the second part, I give an example of the insights given by such spectroscopic characters. So I hope that it can help you gain a more, like I would say, a general picture of how we can use spectroscopy to learn about electronic structure. And of course, in the end, I might also mention a bit some study that combines spectroscopy and machine learning. Yeah, so that will be the content of my today's presentation. Let's start. I just would like to stress of course, one may ask why we need such X-ray spectroscopy to probe the electronic structure. So I give here an example. For example, you know that nowadays the transition metal oxide composites have a very broad application, like in batteries, in supercapacitors, and fuel cells, and all these I would say catalytic materials. And in the processing or in the working mechanism of such materials, we would like to know that, for example, with the battery material during the charging and discharging process, we would like to know how the material structure or how the redox chemistry happens or occurs during the process. And in principle, when you do such kind of dynamic processes, you always expect that there will be like the change of the local symmetry or the orbital occupation. And of course, using X-ray spectroscopy, like more advanced technique, you can even detect the excitations, including like magnons or spin waves. So basically, it provides a very useful tool for us to gain a very deep understanding about I would say the physics that is, or the physical mechanisms that is underlying the or behind the mechanical or not mechanical, the material properties. So that is I would say a general overview of why we need such technique to help us or to help us gain more physical understanding. And with the X-ray spectroscopy, you can see that it actually includes a very wide categories of techniques. For example, we have the time-resolved X-ray absorption spectroscopy, that it will be able to capture the time-dependent structure phase transformation. And we also, if you think about that, you use like a photon to excite an electron from the core level to the unoccupied state, then we have this X-ray near-edge spectroscopy, which can tell you the information about the oxidation state. And for the extended X-ray absorption fine structure, it can tell you more about the basically the local crystal environments of the elements you are probing. And of course, if you go with such resonant elastic X-ray spectroscopy, you can even, I would say, gain more information about such like element selective DD excitation or orbital coupling and splitting. And of course, this map does not cover all the aspects of the X-ray spectroscopies. We also have like a photon emission and fluorescence and so on. So basically, you have quite a series of tools to try to detect the very fine electronic structure in the material. So I here just give a very simple example, like since we have such experimental technique to get the spectroscopy, but on the other hand, why we need theory? the one important aspect is that, okay, we might get such kind of spectroscopies with some line shape, but how you interpret the information embedded in such spectroscopy, that is a more important or challenging problem that for us to tackle. So in principle, we need such theory to first, it allows us to validate the assumptions we make in the model, and understanding also, of course, as well as the understanding we have for the material properties. For example, you might start with a simplified model first, then you observe some like disagreement, then you know that, okay, maybe something is missing, and then the important thing is here is to find that the thing that is missing in this picture. So in this way, we can like gradually deepen our understanding. So usually the routine we take is that we try to understand first, then we try to gain the predictive capability. But actually in practice, it's very hard for us like to use theory as a tool to predict. I would say the answer, I always like to use the quote from the Anderson in his very famous article that more and different. So it tries to understand like why it is hard to predict things from scratch. So he says in the article that the structure of the nature is completely hierarchical. It's built up from emergence upon emergence, but the very concept and categories on which the next stage can take place are themselves arbitrary. So you could think from a single particle to a many particle picture. They don't add up like in a very simplified picture. Instead, when you have like a many body problem, then things to like become complex. So it was also mentioned that the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. So yes, so that is, I would say, maybe an answer from a science philosophy point of view. But if you also check the technical details, like I would show you one case that actually the complexity can grow with exponential scale. I give here an example of the nickel oxide. Think about one unit cell, and if we only like consider one nickel and like one kind of ligand that is some like interacts with the transition metal, you could say that the number of spin orbitals is like the total number of spin orbitals is 16. It is basically consists of 10 d orbitals and 6 p orbitals, for example. And then if we now know that we have 14 electrons in which will be distributed in these 16 spin orbitals, then the number of possible states will be obtained from this binomial coefficient. You can see that when you increase the unit cell, the size of the unit cell, basically this number can become very, very big. And of course, if you think about like just showing this problem just on a classic computer, or anything that is maybe like you will of course suffer from this memory problem on the first point is. So that is something I would say, like when you start to increase the size of your system, then you will basically like run into such a bottleneck when you're trying to solve your problem. But if we start to think about, okay, how we can kind of take a or bypass such type of challenge, you maybe the first thing you would think that maybe we can use quantum computing, because if you think about this many body state, it's like it can map very, very well with the quantum computing. For example, you can solve this 16 spin orbital problem if you have like simply put maybe a 16-qubit quantum computer. Then you can describe your quantum state like extended by the wave function. And that seems to be a like direct solution, but we all know that nowadays the quantum computing is still suffering from, for example, it's the noise, it's very hard to really for you to, for example, design the algorithm and also observe and then get the results. So of course, we still have a long way to go in this direction. And on the other hand, we have I would say, a more realistic method in the current phase that, for example, we can use crystal field theory. So this theory assumes that basically a single atom is embedded in an effective potential. And go beyond the crystal field theory, you can also appeal to the so-called ligand field theory. It can sometimes you can also, it can be also called as charge transfer multiply theory. This theory, it goes one level up than the crystal field theory, because in this theory it also considers a ligand, like a ligand atom that is interacting with the transition metal you are dealing with. And on top of these two theories, you can even go more advanced, like to the more advanced branch that is, you can also use the so-called dynamical mean field theory. Then in this theory, it assumes a more self-consistent way to determine the bus. So compared to the ligand field theory, then the description of the ligand is much more accurate in this dynamic mean field theory. But today I will put my focus mainly on crystal field theory, just to give a, I would say, more generic picture of how it works. For example, here I use this sodium chlorine as crystal as an example. So here this sodium ion is surrounded by six negative charges, and basically the crystal field, you can think it as electrostatic potential generated by the six negative charges described in this way, but you don't have to really put too much focus on the equation now. And actually, the form of the crystal field, it depends on the local symmetry. Basically, if you look at this octahedron, I highlighted using the yellow color here. So the sodium atom, like surrounded by these six negative charges, and depending on the what's their coordination relation is, basically you would think that the field will have a different distribution, which it's kind of governed by the local symmetry. But later I will give a more detailed description on this aspect. So, but here we only in the crystal field, we restrict ourselves to a local model, which is we consider only the first nearest neighbors of this sodium atom. So the symmetry I just stress here. So why is it important? It's a very fundamental principle of the natural world. It's responsible for many physical and spectroscopic properties. And if you're interested, you can also look into the group theory. I have a good recommendation of a book called Group Theory in a Nutshell for physicists. That is a very, I would say, well-written book that even you don't have maybe much experience with group theory, but you can still try to enjoy the content delivered by the book. But in principle, the group theory is it's the thing that relates. Just the things like tells us about the symmetry. So if you can properly use the symmetry information, it will simplify our calculations. And on the other hand, it can predict also some properties. Maybe I can give a very simple example, like how it can predict some properties. So also this example was given in the book, like in the particle physics. I think they have, if you think about the fundamental particles, there was some like particles that belong to the group called SU3, and this group has kind of the dimension of the representation of this group like has 10 dimensions, but at that time only 9 particles are found. But then people will think, okay, actually there is something one missing. Based on this kind of observation, that it's actually, I wouldn't say predict, but it at least tells you that you are missing something. And in the end, people did find a 10th like a particle called Byron. So that is like, I would say the power also of the group theory that tells you how you should look at the problem from the symmetric point of view. But going back to our crystal field Hamiltonian, so in principle, if you now write the crystal field Hamiltonian just in such mathematical equation, so it's basically expanded on normalized spherical harmonics. And we know that basically the spherical harmonics are the eigenstate of the orbital angular momentum in quantum mechanics. So if you think about, for example, this spherical harmonic YKM, when K and M equal to 0, it's a symmetric spherical shape. And if you think about the p orbital of an electron, like when K is equal to 2, M equal to 0, or then the shape of such spherical harmonics are the double shape of the p orbitals. So that is why we can write the crystal Hamiltonian as a kind of linear combination of using such coefficient plus some function with certain symmetries. So that is why it was also stated that the Hamiltonian is like determined, or not determined, but at least it was the local symmetry plays a very important role in describing such crystal field Hamiltonian. So using this octahedron like as an example, so also this sodium chlorine crystal, basically actually this point group is belongs to the so-called OH point group. And if a transition metal that has such OH point group, as you can see that, for example, it has if you look at this C4, it basically means a rotation axis that is along, for example, this C direction. If you rotate the octahedron by 90 degrees, it will go back to itself. So that is basically, for example, in the OH point group, it has like all the symmetry operations that leave the crystal invariant. So that is how we like judge if our crystal belongs to which kind of point group. But using such symmetry information, you can actually very largely simplify the form of the matrix, as you can see here. If you describe this D state using 5 orbitals, like 5D orbitals, now we forget about the spin. So it's 5 orbital with like 5 times 5 times 5 matrix. You can only see that actually only these elements are non-zero, while the other like white part are 0. So in this regard, if you can use such symmetry information, it will simplify I would say how heavy the calculation might be, because now you can just convert the matrix to a more sparse type, which will save you some time when you try to solving the eigenvalue problem, for example. And here, this matrix like is how to say described or written in the spherical harmonics in this basis. But now if you do a base transformation and write it in the so-called real axis, as you can see there, I think maybe you are more familiar with such language, and then the matrix will be diagonal. And you will have found that in this OH point group, you have EG like with 2 a number of 2 degeneracies and also 3 T2G orbitals. And actually, the energy difference between this EG and T2G gives us the so-called 10dQ, which is a quantity that is used to quantify the crystal field splitting. And later, this parameter will be used in our, later I will show you some very simple hands-on modeling for the spectroscopy. So this quantity, I will use it later, but you just need to remember that it actually tells the energy dependence between the EG and T2G orbitals. So, okay, and I just had to describe you what is this Hamiltonian part, but I will not give much details in running through all these details in the equation, but just to mention that basically we need to write the full Hamiltonian, which also includes the electronic interaction part, which is basically described by the Coulomb interaction term, and of course the spin coupling term. And with the form of the, and while this term we don't like kinetic or electronic nuclei interaction, we don't care about it in the spectroscopic calculation. So we only need to write these 3 parts and try to solve the so-called spectroscopic responses. What usually the way we get this is through this Fermi's golden rule. So you have, for example, the initial state, and of course you have also final state. Initial state meaning that before you excite any electron, and final state, of course, is to describe the states that is after the photon interacts with electron. And this transition operator basically gives you, it describes the interaction term between the electron and light. And if you look also at this delta function, basically you could think it as like in a picture that only those photons with a specific energy, like which is the difference between the initial state and final state, will be absorbed to, this is, you can also understand from point of view of course, we know this quantization of energy level, only the certain energy level will be absorbed and used to excite one electron. So that is why we have delta function here, while this part gives the probability, which is also the intensity of the response in the spectroscopy. Yeah, so now I maybe just give a very simple example using the so-called CRISPR code. So this is a graphical interface designed for the code quantity. And later I will also give the reference to the quantity website, but you can, for example, if you now want to set up, we use the Nico 2+ as an example. So you can choose basically different element type and the valence, the formal valence state of the transition metal. And here is for the point group. I think now it's only like those which are more commonly seen in the crystals are listed. Okay, so for this, you could choose like you want to calculate X-ray absorption spectroscopy or photoemission or emission. But here I will choose XAS. And here is basically the age of the spectroscopy. For example, if I choose L23, it means that I excite the 2p core electron to the 3D valence states. So that is like what this age indicates. This temperature really don't need to, like we can just leave it as it be. Then, okay, for this part, we have this Hamiltonian setup. So you can, now we click this crystal field and you can see that we need to type in this 10dQ parameter. So usually the way we obtain such parameter is, of course, the first you can search for some literature and try to check the value. And on the other hand, in this, you can also use ab initio input to get this value and maybe at least as a starting point and try to tune the parameter to fit with experimental observations. So, I mean, for the crystal field, there's not much actually to set up. After you give these parameters, then you can just run this, and you will see the basically the X-ray spectroscopy, X-ray ENCCS spectroscopy of the Nico 2+. And on the other hand, you can, like, there is also a function that you can save the input as this same quantity input. Like, basically, I will not show it here, but if you save it, it will be a Lua script that used by quantity for the calculation. But the purpose here that you have some starting point, maybe you want to fine tune or you want to modify the input of your Hamiltonian, so you can download it, save it as a script, and do some manual change here. So, but here I want to mainly, I have some like preparations for the examples I give here. So this is the figure I cut from a published paper. As you can see that the first, like this first curve is actually the experimental results. While if you just, for example, now if you set 10^3 equal to 1.65, I would say if you compare the simulation and experiment, they agree already quite well. But here the paper also mentions some very subtle difference on the second peak, that if you do not include the exchange coupling, basically because you could think that the Nico, it has the Nico atoms surrounding imposes an exchange field that is caused by the spin interaction among the Nico atoms. So if you do not include that term in your Hamiltonian, then you might get something like with the first peak like slightly higher than second. Sorry. So without exchange, you would see that the two splitted peaks are more or less at the same magnitude, while if you include exchange, which is actually more accurate, then you will see such kind of like the first peak gets higher, which fits better with experimental results. So, I mean, from this example, you could see that it's really sometimes can be very subtle details that, and of course, you can also play with the parameters and try to see what kind of effect it will have. But just one, I would say some questions or just some intuitions you can get from such kind of spectroscopy is that you could actually use the so-called sum rules to get the number of occupancies here. Because if you think that for the X-ray absorption spectroscopy, we excite the 2p core electrons to the valence, then the number of occupations, of course, will be proportion to the number of vacancies we have. Otherwise, if these states are fully occupied, then there will be, I would say, almost no space for these core electrons to be excited there. And another observation you can find or see from the figure is that this L3 peak, like the first main peak, is much higher than the second. That's because if you think about like for the p electron with spin-orbit coupling, it will split into the J equal to 1/2 and 3/2. So for the 1/2 orbital, it contains two 2p electrons, while for this 3/2, it contains 4 2p electrons. And that this kind of like population difference gives rise to the response difference, as you can see from this figure. So, but of course, this is, I would say, very surface or superficial or very surface observations. But I just want to maybe mention here to give you a feeling of how you can try to like interpret such kind of spectroscopies. Yeah, so then you may argue that, okay, it seems that currently the crystal field model is already quite accurate. Then why do we need HPC resources? As you can see, actually, first the fine structures are missing. We are using a very simplified model, and we are missing out some maybe important physical details. And here because I first give an example of X-ray absorption, but in the case of photo emission, that you, for example, you excite one core electron to the vacuum, then this is not any more charge conservative case. And in such kind of XPS spectroscopy, you could see that you would find like a second peak near the main peak. If you just simply still use the crystal field model, even ligand field model, you cannot reproduce such feature. So this peak, like this small peak, is caused by the so-called non-local screening effect. That is, if you consider only I would say the charge transfer from the neighboring nickel and also from the ligand to the nickel atom, then in this regard, you can capture this very fine feature appeared in the spectroscopy. So in this regard, you have to really go beyond the crystal field theory and use the so-called dynamic mean field theory. And actually, for this kind of calculation, it will be really, like I would say, resource demanding, and also time. The cost of time is also rather high. But besides that, if you even use, for example, the crystal field model or ligand field model, where you have to now basically increase or include the ligand orbital, then you can imagine that the dimension of your matrix will be enlarged. So in this case, if you just still use, for example, one CPU core to do your calculation, it might take some time for it to finish. So then basically you could still use or utilize the HPC as a way to also empower yourself with the like multi or parallel computing. So actually the quantity, I mean, basically all the calculations I show here, at least conducted by me, I use the so-called quantity code, and the crispy software I just introduced you can also like export the input in the quantity format and run it with the code. And this quantity code, you can actually, it adopts such OpenMP shared memory parallelization. So if you look at this scaling behavior of quantity, although, I mean, here I use still a small system just to test, to benchmark the scaling behavior, but you can see that by using multiple threads, you can like greatly decrease the computational time you would need for one single calculation. In the end, I would like to give an example of the insights we can get from some such spectroscopy studies. So here I mainly use the battery example because in the battery, especially in the charging and discharging process, we would like to know more about its redox chemistry, like knowing about like which element is participating in such redox chemistry will have a big effect on its properties, including the voltage and also the capacity. So that is why we are interested in like what is exactly happening in such kind of charging or discharging, or you could also say it when the lithium is removed or inserted back into the cathode materials. So here we first focus on the cathode material, which is a lithium nickel manganese cobalt based battery cathode. And what we found experimentally is that with the charging process, you could, or with the lithium like removed from this cathode material, the satellite peak near the main peak get reduced. And we would like to understand what causes such type of reduction in the satellite peak intensity. And here we use the ligand field model, which, as you can see, that we consider actually the ligand and to the transition metal charge transfer effect. So our conclusion is that first we did a like dynamic mean field theory calculation to get the probability distribution, or like, for example, how much, what is the fraction of like nickel 2 plus or nickel 3 plus, because you can think that when you start to remove the lithium atom in the crystal, and then the local environment of nickel or cobalt and manganese, they start to change. So we first look at like how the distribution of different formal valence states of nickel changes with different lithium concentration in the crystal. And then with such population of different formal like different valence states of nickel, we calculate its like the, for example, the XPS spectra corresponding to the nickel 2 plus, 3 plus, and 4 plus. And by summing up the, like by getting the weighted sum of this XPS using the information of the population I mentioned in the last slide, we could actually replicate the trend that, if you can see that basically the scatters are the experimental results, the solid lines are the simulation. So you could see that we could reproduce such kind of reduction. But of course, there is some, it's not like 100% perfect match, but I should remind you that also in the simulation, you have other, like you have parameter like broadening, basically to like, how to say, to tune or maybe to give you a different magnitude. But the main message we want to convey here, of course, is first we pay more attention to the trend instead of the absolute value. But one sentence summary is that basically we can use the like the combined tools packages, for example, this simulation of spectroscopy and also the calculation of electronic structure regarding the specific probability corresponding to different configurations. We can try to like confirm or at least validate some of our understanding in the battery material for the redox chemistry. And okay, so this is, I would say, then the part that I promised maybe to give a little bit overview about the application of machine learning in the spectroscopy. For example, usually the machine learning model can be used to map the structure to the spectra. It can be used as like prediction or structure reconstruction. And of course, also like real-time spectral analysis, active learning, or physics-informed machine learning, or even automatic peak fitting or deconvolution to check, to like, how to say, like to dissolve different contributions from different formal valence states. So that is some like applications you can find from current literature. I just give a very example like conducted by me, by a colleague of mine and me. So we here, this example is the so-called adversarial Bayesian optimization. The main purpose of this study is to increase the sampling profits, because in conventional like XAS measurement, you need to do an energy scan to get the spectroscopy. But in this ABO, like this adversarial Bayesian implementation, you could increase its efficiency, like using, for example, only 20 energy points to recover the whole spectroscopy. So the main idea is that it designs these two kind of competing parts called fitting BO and sampling BO. So the sampling Bayesian optimization in the training process will try to maximize the loss while defeating Bayesian optimization, which we also embed the physical model, that is the quantity model, like with the Hamiltonian, we have constructed into the fitting part as well. It will try to minimize the loss function derived here, like the difference between the experiment and the quantity output. So after this process, we first, if you look at the results, you can see that all this basically this black points are those that is mirrored, you could say, think in this way, and with around, I think it should be around 25 sampling point at this figure C, then we could already get like recover the full spectroscopy. And at the same time, we are also fitting the Hamiltonian, meaning that we don't have to rely on the empirical parameter input in the quantity script. Instead, we can also add, like, by this kind of active learning process, we can simultaneously obtain the like physically meaningful physical parameters for such model. So that is, I would say, a very maybe, I don't know, like not simple, but yeah, just some example for you to get an idea of how machine learning can be applied in such in the spectroscopy or in related research topics. Okay, I think that is basically all from my today's presentation. And in the end, I just want to stress a bit that, of course, we know that the spectroscopy measurements are the keys for us to understand the electronics of the structure of matters. And today, I mean, my talk today just scratches the surface of it. But of course, this we want the theory, of course, to help us to understand these features, but it is powerful, but it's, of course, not a magical tool. We cannot really use a very simple, sometimes maybe a simple model works, but in the most of the time, we have to appeal to more advanced theoretical method to uncover the mysteries. But I think that is also the fun part, that you actually, like, you're trying to find the missing pieces to achieve a better understanding of the physics. Yeah, so I think I will end today's presentation, and I welcome for your questions and comments.